Hi, my name is Alex and I study at La Polytechnica. Right now I am studying a degree in electronical and automatical engineering. Today I am going to talk to you about motion planning and obstacle avoidance in non-holonomic robots. My presentation is going to be divided into two parts, which are motion planning and obstacle avoidance. So to begin with, I'm going to talk to you about motion planning, and inside motion planning I'm going to talk to you about three things: the creating of a path, a little bit about steering, and about the different robots that we have nowadays, the most common ones. So, computing a path. To compute a path, first we must understand what is a non-holonomic robot. So, a non-holonomic robot, it's a robot that cannot move to its maximum degrees of liberty, which means it cannot move into every direction. For example, a car. A car can only move forward or backwards and turn a little bit. It cannot move sideways and upward or downward. So a car would be a perfect example of a non-holonomic vehicle. And then, when it comes to computing path, we also have to take into account the kinematic restraints. So for example, slipping. A car cannot turn at a very high speed, and neither can a robot, because if it turns too fast, it will slip. So once we have the non-holonomic restraints and the equation of the non-holonomic restraints and the equations of the kinematic restraints, what we do is we take a field of vectors departing from the robot, and those field of vectors are given from the kinematic restraints and the non-holonomic restraints, and they represent where the robot can move next. And inside that field of vectors, the robot is said to be small time controllable. And when it comes to computing a path, what we have to do is take a finite sequence of those small controllable vectors and line them up from the robot to its target. And of course, when we are computing the path, we take into account the obstacles that are pre-planned, which means that we already know where they are. And now I'm going to talk to you a little bit about steering. So basically, steering is finding the optimal path between you and your target, because sometimes the path is not just straight like this. You need little curves to go as fast as you can. And now I'm going to talk to you about the different types of robots that we usually use, which is the differentially driven robot, which is the simplest one of them all, which is just two wheels. Then we have the differentially driven robot towing one or more trailers, which make the steering a little bit more complicated. And then we have the car-like robot that has four wheels, but can only steer its front wheels. And then we have the bi-steerable robot that is similar to a car-like robot but can steer its four wheels. So to every one of those robots, there are methods and we already know they're small time controllability vectors, and it's very easy to create compute paths with them. Then there are other robots that use approximations from these robots. So now, I'm going to move on to obstacle avoidance. So you might be wondering why we need to move on to obstacle avoidance if it seems that motion planning can avoid the obstacles just as well. Well, what happens in obstacle avoidance is that we avoid not pre-known obstacles, but obstacles that appear as the robot is moving. So for that, we are going to need three main things. One is the obstacle avoidance technique. Two is how the sensor takes into account the shape, the dynamics, and the kinematics of the robot. And three is integration of the environment, the scenario where the robot moves. So first of all, into the obstacle avoidance, talking about obstacle avoidance, there are several techniques. One of them, for example, is the potential field technique. What this technique does is it takes the target of the robot and uses it as an attractive field for the robot, and it takes the obstacles that the sensor catches, and they act as a repellent field. So you take the force of the repellent field created from the obstacle and the force of the attractive field created from the target, and you get a result force that shows the best direction where the robot can move, avoiding the obstacle while moving to the target. Then we also have the vector field histogram. What it does is make a big sensor, make a big circle around the robot with vectors that point to the end of each obstacle. So you get a circle divided by many sectors, and every sector points where there is an obstacle and when there is not, where there is no obstacle. And looking where the goal is, the robot chooses the best direction. Now, there are other methods, but these are the main ones in obstacle avoidance. Now, moving on to the shape, dynamics, and kinematics of the robot taken into account by the sensor. So here there's one very simple method, that is abstraction of these 3 points. So what this method does, it takes the pre-constructed path where motion planning was used, and it takes the shape, the kinematics, and the dynamics, and it takes it into account when reconstructing the path for the robot to go through the obstacles. And last, we have the integration of the field. So here we use one of the most common methods used is the band system. What the band system does is it takes the band of the pre-constructed path and makes the robot go along it. And what happens is that when the robot finds an obstacle, the band is repelled. And that is how the robot navigates safely. So, as you might have noticed, basically all these 3 points focus almost all on the same thing, which is avoiding the obstacles by using a sensor, which is the core point of obstacle avoidance. And now that we come at an end, in the conclusion. Nowadays, motion planning and obstacle avoidance has reached a very high level in environments that are known, like museums and parks and places where the plan is known. But there is still a lot of work to do when it comes to outside environments where there can be so many unknown obstacles. My name is Alex Brett, and thanks for watching.